All right, today let's talk about electron spin. Well, spin was discovered after the famous Stern-Gerlach experiment way back in 1922. In this experiment, they have a furnace that they use to heat up silver, and then they shoot out a beam of silver atoms. Okay, so here comes the beam of silver atoms down this way, and then it goes through a magnetic field. And in fact, it's not a uniform magnetic field, it's a magnetic field gradient. And this magnetic field causes the beam of silver atoms to split and go along two paths, which is very interesting because classically you would not expect it to bunch into two dots at the detector, but to have a continuum of possible places where it lands. But instead of this continuum, you get only two possible values. So here's the actual result in 5 compared to the expected result in number 4. And so there was a quantization of the deflection in a magnetic field, which was not understood or not expected, but obviously some kind of quantum effect. And this experiment led to the understanding of spin. So let's ask, why would a silver atom even be deflected by a magnetic field gradient at all? Well, you might think, well, it's an atom, and atoms have electrons, and electrons are moving around. And if I have a very simple mental image of like a Bohr atom, where electrons kind of spinning around a nucleus, then I've got an electron moving in a circuit, and that, we know, can create a magnetic field. So is that what's going on? Well, let's think about the electron configuration of silver atom. It's got a krypton core, and then it's 5s1, 4d10. Remember, this is one of those exceptions where to fill a d subshell, we actually steal one of the electrons that normally would have gone into an s orbital. And so it's s1d10 because of the extra stability of the d subshell. All right, would we expect that to create a magnetic moment that could get deflected in a magnetic field? Well, anytime I fill a subshell, so put 2 electrons in an s orbital, or 6 electrons in a p orbital, or 10 electrons in a d orbital, or 14 electrons in an f orbital, that winds up contributing a total orbital angular momentum of L equals 0. So even though a p orbital has an angular momentum of L equals 1, when I add 6 p electrons, they all cancel each other. So anything that's filled gives you no net angular momentum. So the krypton core is filled and gives no net angular momentum. The 4d10 fills the d subshell and gives no net angular momentum. And all I've got left is 1 electron that's unpaired in an s orbital. But because it's an s orbital, which has L equals 0, that contributes to total L of a contribution of 0. And so there just is no net orbital angular momentum in silver atom if it's in its normal ground state. And so we wouldn't expect any magnetic moment to occur because whatever circulation of electrons is happening, it's done in a symmetric, spherically symmetric way. And so any magnetic moment that would be created would be canceling itself as the electrons are all spherically symmetric. So total orbital angular momentum is 0, and we wouldn't necessarily expect a magnetic moment out of the orbital motion of the electrons around the nucleus. But obviously there is a magnetic moment somehow, because the silver atoms are being deflected in the magnetic field. So where is it coming from? Well, the postulate was that the electron is considered to have an intrinsic or built-in magnetic moment due to a built-in angular momentum that is somehow a different angular momentum than orbiting around the nucleus. And that angular momentum was given the name of spin. And if you like to get a sort of a hand-wavy idea of what is going on, you might kind of imagine that an electron is sort of spinning around its own axis, and it can spin kind of clockwise or counterclockwise, and result in a magnetic moment pointing kind of up or down, depending on which way it's spinning. Now, this is a very hand-wavy thing. Sometimes you see this in textbooks. There's a problem with this, and one is, if an electron were modeled as a point charge, then it has zero width, and so spinning around your own axis doesn't really make sense. Maybe it does make sense if we think about the electron not being modeled as a point charge, but having some finite size, which of course it does, although it's very small. But the spinning around your own axis idea, it might give you some kind of intuitive feel, but I think physicists don't believe that this is literally what's happening. It's somehow just a built-in angular momentum that is there, and it is hard to kind of draw an easy picture for that would hold up under intense scrutiny. Furthermore, the spin is quantized because it's a small particle governed by the laws of quantum mechanics. So the size of the angular momentum, the magnitude of the angular momentum, is quantized, and so is its projection on the z-axis. So that is going to be very relevant. So you could kind of imagine maybe thinking about this angular momentum for a second. If you think about classical angular momentum, well, then you have an angular momentum if you have something, a vector sort of precessing around an axis. So here's a vector precessing around the z-axis in such a way that its projection on the z-axis is constant, okay? And so it has a well-defined projection on the z-axis, and that is going to be what we're going to call our spin-up case for an electron, or an alpha spin. And the projection is h bar over 2, and it's positive for an alpha spin. And we could also have a beta spin possibility where the projection on the z-axis is well defined, but it's negative h bar over 2, okay? And it turns out that the length of this vector that we imagine is precessing around the z-axis winds up being h bar times the square root of 3 over 4. And I'll say more about that in a second. So at any given point in time, exactly where you are at on the x or the y-axis may be uncertain, but if you're in an alpha spin state, it is certain that you're got a projection of plus h bar over 2 on the z-axis, and if you're in a beta spin state, you've got a projection of minus h bar over 2. And if you like, connecting to that earlier picture, you could kind of imagine maybe the spin up is maybe rotating sort of counterclockwise, and maybe the spin down is rotating kind of clockwise around the z-axis. And they both have the same length of this vector, so the same magnitude of the angular momentum, but it's either sort of pointed up along the z-axis or down. Okay, there's a kind of a little bit of a picture of what's going on. So I already mentioned the magnitude, and I'll connect that to a general formula in a second. Here we go. So in general, for a spin angular momentum, the length of the vector that you can consider precessing around the z-axis is h bar times the square root of s times s plus 1, where s is a spin quantum number, and that has to be either an integer or a half integer. And for a single electron, it's always exactly s equals a half. And that's why I plugged in s equals a half, got a half times a half plus 1, so that's a half times 3 halves, which is 3/4, and that's inside the square root sign. So that's why I know the length of this vector. Whether it's spin up or spin down, same length. And the projection can either be plus or minus h bar over 2. Now that's for a single electron, okay? And because I had one unpaired electron in the Stern-Gerlach experiment, it could have a spin associated with it, and that could cause a deflection. But how do things play out if I've got more than one electron going on? Well, you can kind of think of it as a vector sum. The total spin is kind of like a vector sum of all the individual spins of the electrons. Now this is actually a bit of an oversimplification. What we really need to do is use spin operators rather than spin vectors, and you could look this up if you find a graduate textbook in quantum mechanics. But for illustration purposes, let me think for a second about vector sums. But the vector sum is a very special vector sum. It's a vector sum where the addition is quantized such that the length of the vector is this formula I just gave on the previous slide, with the additional constraint that s can either be an integer or a half integer. And the additional constraint that the projection on the z-axis is going to be a number called m sub s. I guess it's actually m sub s times h bar, where m sub s is goes from minus s to minus s plus 1, etc., add 1 each time until you eventually get up to positive s. So it goes from minus s to plus s in unit steps of 1. That times h bar is the projection on the z-axis. So it's a very highly constrained sort of vector sum. Now, what is this quantum number m sub s for the total atom or molecule? Well, getting that is very, very easy. All you do is add the m sub s's for each electron, and they're either plus a half or minus a half for each electron. So I just add a whole series of plus a half, minus a half, plus a half, minus a half, until I've added up all the electrons. And because each alpha spin is plus a half and each beta spin is minus a half, if you want, you can rewrite this formula in what I think is a little bit easier way, and just say, well, each plus a half, or each alpha spin gives me a plus a half, and I have, say, n alpha of those, and each beta spin gives me minus a half, and I have, say, n beta of those. And so if I add up all the alpha spins, I'll get a total of n alpha divided by 2. And if I add up all the beta spins, I'll get a total of minus n beta over 2. And the sum is just this. So if I had an equal number of alpha and beta spins, obviously their projections on the z-axis cancel, because n alpha equals n beta, and I get 0 divided by 2. But if I had, say, one more alpha spin than beta spin, then there would be one spin that doesn't cancel, and that alpha spin has a projection of plus a half, and so the total would have a projection of plus a half, because I'd have one more here than I had there. Okay, so that's pretty easy. If you knew the spin of all your electrons, then it's pretty easy to know what the projection on the z-axis of the total spin is. What about the total spin quantum number s? Well, this is inherently more difficult. You need to do a kind of a vector sum, and it's really a vector sum over operators, even not just vectors. And you need to keep quantization rules constant. So this is a little non-trivial. And if you wanted to know how this really works, then there's usually a chapter about addition of angular momenta, which is a general topic which would cover both orbital angular momentum as well as spin angular momentum in graduate level textbooks. In fact, sometimes there are even entire textbooks talking about how to add angular momenta. For example, Zer's book on angular momentum would be one place to look. And I'm, in this introduction, going to gloss over all the details. But I will try to give you a few cartoons to try to illustrate some of the key concepts. And let's just look at only 2 electrons to try to keep our lives easy. However, the diagrams I'm going to draw, I'm going to pretend that I am doing a vector addition. And as I've tried to hint already, it's not literally a vector addition of vectors in 3D space. These spin vectors are more abstract quantities than that. So they're not literally vectors in 3-dimensional Cartesian space. And so I am going to draw some 3D vectors adding to be able to try to illustrate something and convey some of what's going on. But the spin vectors, not actually 3D vectors. And in fact, instead of a linear vector space in x, y, and z coordinates, I'm really going to be dealing with direct product spaces, where I have spaces of alpha times alpha or alpha times beta, and these vector spaces are going to involve inherently 2 electrons, and the space is a 2-electron space, not a 3D vector space. So for the illustration purposes, we'll draw some 3D vectors, but my point is, don't read too much into them, because that's not literally what's happening. Okay, so let me draw my 3D vectors to partially convey what's going on. Suppose I have 2 alpha spins, and really probably I should write alpha times alpha would be probably a more accurate way to put this, but anyway. So here's an alpha spin. And I've got this, vector processing around the z-axis. Okay, I know its length because it's 1 electron. I know its projection is plus h bar over 2 because I said it was alpha. And the other electron's also alpha, so it's the same deal. And then I'm going to do a kind of a vector sum of these guys. Well, if they're both pointing up, then the vector sum will be pointing up. And if the z projections are both positive 1/2, then the total vector sum of these will have a z projection of twice that. So plus h bar comes out of adding 2 plus h bars over 2. So I hope that part makes good intuitive sense anyway. Now the length of the vector, you might think if I add them totally as literal vector additions, would just be twice this. So what would that be? I could simplify this, take the 4 out of the square root. I'd get square root of 3 over 2, and 2 of those would be square root of 3. But this is actually square root of 2, so that's where my little vector sum idea is kind of breaking down, because it's not literally what's happening. But you could realize that maybe these shouldn't quite add, because I did say we have to follow this quantization rule that the length has to be h bar times square root of s times s plus 1, and s has to be an integer or a half integer. If I were to try to add these literally and get square root of 3, that doesn't match square root of s times s plus 1, where s is an integer or half integer. So that wouldn't be allowed. It wouldn't fit the quantization. But this does fit, and it does turn out that the length of this guy obviously can't be bigger than the length of this plus the length of that. And so, that's a good thing. But it turns out this does fit the pattern of square root of s times s plus 1 if s equals 1. And notice there's a nice little feature here. S equals 1 matches the addition of 2 s equal a half. So half plus a half gives me 1. And so there is a nice kind of addition property with the s's. So that's cool. I'll also mention, I added a half plus a half and got 1. And you can see that obviously if the projection equals this formula, m sub s times h bar, that works as long as m sub s is plus 1. And that fits the formula I gave you a minute ago. I said take the number of alpha electrons minus the number of beta electrons divided by 2. So here there's 2 alpha electrons, and there are no beta electrons, so 2 minus 0 is 2, divided by 2 is 1, and so this formula matches that formula. So everything is cool with just adding and subtracting plus and minus the halves to get the z projection part. That's the easy part. All right, now let's think about the case where I have two beta spins, okay? So here's my cartoons for those guys. The lengths are the same, but now they're both pointed down or have a negative projection on the z-axis. And the projection on the z-axis works the same way as before now, but just with minus signs. So this guy is a minus a half, this guy is a minus a half. You add those, you can get minus 1 times h bar, so that's great. And again, this formula still works because now I have two beta spins and 0 alpha spins, so 0 minus 2 divided by 2 is minus 1, which matches the coefficient in front of h bar here, so big M sub s is minus 1, so that's cool. And again, the length of this vector that results when I add these two vectors is the same as it was on the previous slide, and it's just now pointed down instead of up. But again, I took two s equals 1/2 electrons, added them to get a total angular momentum vector with s equals 1. So that is perfectly fine. Now those are the two easy cases. What about the harder cases? Well, you could try to add alpha plus beta. Okay, and again it's really alpha times beta, which I'm glossing over in the purpose of trying to give you a simple illustration. But suppose you try to add these two vectors that are precessing around the z-axis in such a way that they stay in phase as they're both rotating around the z-axis. And if they stay in phase in their precession, then if they're the way I've drawn them here, then the y, or I guess I should say the z projection cancels, because this is pointed up, this is pointed down, they have the same instantaneous location around the xy plane, and so they cancel each other, and they're pointed, I guess in this case, kind of the vector's coming out of the page at me. And then if they keep precessing around in phase, then they'll trace out a circle around the xy plane, like this, in which the z component perfectly cancels, so there is no z part here, and I just get the net vector rotating around in the xy plane. And how long is that vector? Well, again, it has to fit this formula using an integer for, or a half integer for s, and it turns out, again, if I add two s equals 1/2 electrons, I get a total vector that matches this formula with s equals 1. So I essentially can add the two s's and get this guy, at least in this case. So the length is h bar times square root of 2, and it just rotates around the xy plane. Now what about the projection? Well, I said the z part cancels, so it has a length m sub s times h bar as the general formula, and that will work as long as I assume now m sub s equals 0. Does that fit my general formula? Yes, it does. I have one alpha electron, one beta electron, they cancel and give me 0, so everything is totally consistent. Okay, interesting. Now, there is another possibility. These two vectors could be precessing around in such a way that it looks like this, where now, instead of staying in phase where the z part cancels, but I get a net direction along x or y, now I'm going to have them go in opposite directions along x and y as well, so that the xy part cancels, and so I have a total cancellation of these guys. So if you like, they're kind of out of phase with respect to x and y. So the xy part cancels, the z part also cancels, and I get just nothing. I get complete cancellation of these two vectors. This will still fit my general formula if I use s equals 0 now to get the 0 length, and then the projection is obviously also 0, which still fits one alpha and one beta electron canceling and giving me nothing. So that is a fourth possibility for the addition of two spins. So let me summarize what my final spin angular momentum can be after I add these two spins for two electrons. They could both add kind of constructively and both point up, and that gives me this one. They could both add constructively and both point down, and that gives me this one. Or they could add constructively with respect to the xy plane, but cancel with respect to the z direction, and that gives me this one. And here you see they're all s equals 1. So you added two s equals 1/2 electrons, you got a total of s equals 1, but that guy could be pointing up or in the xy plane or down. And so you have three possible results for m sub s, the projection along the z-axis. And this is called a triplet because there's three of them. And you notice that the m sub s does fit a formula I gave a few slides back. I said it can range from positive s to negative s in steps of 1. And that's definitely what happens here. It can go from minus s to 0 to plus s. It kept taking a step of 1 each time, and that totally fits the rules. So everything is okay with these three. And then I did have that fourth possibility where there's a complete cancellation of the vectors, and that means there is no spin, so s equals 0, and 0 projected on the z-axis is 0, and this is called a singlet coupling, and it's singlet because there's one possibility. So if I had two spins, they can add together in 4 possible ways, and here are the 4 possible ways. Okay. And I didn't just mention this. It does fit this m sub s ranges from minus s to plus s formula here and here. This is trivial, but they all fit this. So let me talk more about this m sub s, going from minus s to plus s, and introduce what's called the spin multiplicity. So let's just make a little table of the first few possibilities for s. And remember, s can be an integer or a half integer. So if s is 0, m sub s must be 0. That's a kind of a boring one, and that's called a singlet. And what's the multiplicity? The multiplicity is the number of possible values for m sub s. Okay? So it turns out this has the general form of 2s plus 1. Now if s is 0, then 2 times 0 plus 1 is 1. There's only one possible way to have m sub s, so that's a singlet. But now think about this next one. If s equals 1/2, then that's one electron. It can point up, it can point down. So m sub s is plus 1/2 or minus 1/2. That's a doublet because there's two possibilities. And because there are two possibilities, the multiplicity is 2. And that does fit. 2 times 1/2 is 1, plus 1 is 2. The triplet, we saw an example of that. That's if s equals 1. Now m sub s could be minus 1 or 0 or 1, so there's 3 possibilities. So it's a triplet with a multiplicity of 3. If you're at s equals 3/2, then you can go minus 3/2, minus 1/2, plus 1/2, 3/2. Notice this one doesn't go through 0, neither did that one, because you have to have unit jumps. Because there are 4 possibilities, it's called a quartet, and the multiplicity is 4, and it does fit this formula. And let me list one more. If s equals 2, then you go minus 2, minus 1, 0, 1, or 2. 5 of those called a quintet. Okay, and you could keep going. You could go to sextet, septet, octet, nonet, and those are all possible, but increasingly unlikely unless you have some high-spin metals or something. The reason I want to stop and stress this slide is because this number, the spin multiplicity, is what the user must enter into a quantum chemistry program when you want to run a quantum chemistry calculation. And the program doesn't know what to put, so the user has to put it. And so that's why we have to know a little bit about spin. So how does the user know what to put into the program if it is this important? Well, let's do a few examples, okay? The general principle is that two electrons paired in an orbital, one alpha, one beta, will singlet couple and will cancel each other out. So their contribution to S and their contribution to M sub S is 0. So basically you can ignore them. So this is really good. So only open shells, only orbitals with unpaired electrons matter if you're trying to determine S. So let's do an example of the hydrogen atom. The electron configuration is 1s1. So there's a picture of that. And for a single electron, I've already said a single electron always has S equals a half, and M sub S can be plus or minus a half in general for one electron. By convention, if you're getting ready to put something in a quantum chemistry program, you normally pick alpha as the one that you think about if you have to pick something. So we'll pick alpha, and so that means M sub S is positive a half. And so I have M sub S is positive a half, S equals a half, and that's what I'm going to think about when I think about hydrogen atom. Now what do I put in the program? Well, actually for the program, M sub S, it'll pick alpha spin, but the user doesn't have to say that. The program will just do that part. But you do need the multiplicity. So what is the multiplicity? Well, if S equals a half, the multiplicity is 2S plus 1. So 2 times a half is 1 plus 1 is 2. That's true. And here, even though I've used little s and little M sub S to mean for a single electron, because there is no other electron to couple to, the total spin and its projection are the same as they are for the individual electron, because there's only one electron. So, no vector addition to worry about. I just translate the result from one electron to the overall atom, and I'm done. So it's a doublet because M sub S could be plus or minus a half. The calculation will actually use plus a half, but the user enters 2s plus 1, which is 2. So that's fine. How about helium? Well, its electron configuration is 1s2. So there we go. And now in principle there is a vector addition because we've got 2 spins and they could couple in different ways. However, as I said a couple slides ago, anytime electrons are paired, one alpha, one beta, in the same orbital, then they wind up singlet coupling and they don't contribute to an overall spin angular momentum. So this is a singlet, and for a singlet, S equals 0, M sub S has to be 0 in that case. 2s plus 1, plug in 0 here, 2 times 0 plus 1 is 1. It's a singlet, there's one possibility for the z projection of the total spin, and so you enter a 1 into the quantum chemistry program. And fortunately in chemistry a lot of things have electrons all paired up, and so this is the most common case, and we only have to worry about it when this is not the case. How about carbon atom as an interesting example? Well, the electron configuration is 1s2, 2s2, 2p2. The 1s2 and 2s2 fill the subshells, and so they don't matter for determining spin. So just forget about those for a second. The 2p2 does matter because it doesn't fill the subshell. Hund's rule says keep those electrons unpaired as I start to fill up the 2p subshell. So here's a little diagram. I filled that, he doesn't matter. I filled that, he doesn't matter. I've only got 2 electrons. The 2p subshell could take 6, so this is unfilled, so I need to worry about this part. And Hun says start putting down alpha electrons first until you have to track back and then start pairing them, but that doesn't happen for carbon. I've only got 2. So it looks like that. And again, by convention, when I draw these diagrams, I'll typically start putting alphas instead of betas, just because that's kind of the arbitrary choice we make. The programs wind up also doing the same thing internally. But for right now, I just need to determine what spin this is. And if I have 2 alpha electrons that are not paired up, if they're in unpaired orbitals, then it winds up that this contributes to a triplet case And you can see that the way I've drawn this, if you've got an alpha and you add those two alphas, you'll get a total m sub s of a half plus a half equals 1. So m sub s equals 1. And where could I get a thing like that from? Well, I certainly could get it from a triplet. And if you've got a simple situation like this, then that is where you expect it to come from. So we expect this is a triplet. The two little s equals a halves add to give a big S equals 1. And there we go. Okay, so we'll pick that for carbon atom. And if I wanted to run a calculation on carbon atom, then in the program I would input 2s plus 1. If s equals 1, then plug that in, and I get 3, so I would tell it, hey, it's a triplet. So let me see if I can summarize where we're at so far in determining spin. If I have two electrons paired in an orbital, one alpha, one beta, it doesn't matter, and I just get a singlet. If I have only one unpaired electron, then little s equals a half and big S equals a half because there's nothing else going on, and then plug this into this formula and I get 2. So it's a doublet. If there are multiple unpaired electrons in same energy orbitals, degenerate orbitals, Hun says expect to have the high spin case. Don't pair them up until you have to. And we would expect that however many unpaired electrons are all alpha spins pointing up, and they couple together to give me a net S. That's the sum of all the 1/2s from each of those unpaired electrons when they add together. Okay? So you do that, and you'll expect the lowest energy case to be the one where S equals m sub s, which equals the number of alpha electrons minus the number of beta electrons divided by 2. And before, when I did carbon, I had, let's say, just worry about the two p's because I know the other ones cancel, 2 unpaired electrons that are both alpha, 0 unpaired electrons that are beta. So I had 2 minus 0 divided by 2 is 1, and that is what I had for carbon. I had S equals 1. Now that's not what you put in the program. You put in 2s plus 1, and so you would compute that. And I had 3 for carbon. I will caution you, Hund is not always right. There are some cases where the Hund's rule is violated. I'll say a little bit about that in part 2 of my spin talk. And so it's not irrelevant to learn some of the more advanced mathematics of how do you really couple spins, which I'm kind of glossing over in this talk. But as a rule of thumb, Hund is often correct. And I will point out in part 2 some cases where the Hund's rule doesn't work. So to try to summarize what I've just said, if I have plain, boring, normal molecules where all the electrons are paired in single bonds or double bonds or lone pairs, everything's paired up, so they're all singlets. So S equals 0, n sub s equals 0, 2s plus 1 equals 1, and you put a 1 in the quantum chemistry program. So hopefully you have a bunch of these and life is easy. If you had radicals, radicals are chemical species with one unpaired electron, and that's often denoted in a chemical structure with a dot, and the dot means one unpaired electron. Then if there's exactly one unpaired electron, then everything else pairs up and cancels and doesn't matter. So the unpaired one gives you S equals a half, m sub s equals a half, 2s plus 1 is 2, it's a doublet. So that takes care of most molecules. Either they're typically closed shells or maybe they're radicals, and that will account for a vast majority of cases. And let me just give one counterexample from O2. So if I show the molecular orbital diagram of O2, then I use Hund's rule, so the atomic orbitals from each atom are on the left and the right. The middle is the molecular orbitals. I use Hund's rule and I just fill them up going from the bottom and going up towards the top until I run out of electrons. I've not shown the 1s orbitals combining to form 1 sigma g and 1 sigma u star. But here we start with the valence electrons, so I fill these guys, and I fill this, and that, and I finally have 2 electrons left, and I listen to Hund, who says don't pair these up until you have to, and I don't have to here. I can put one here and one here. And so that would give me an m sub s total of a half plus a half equals 1, and I would expect in simple cases that to correspond to s equals 1, a triplet state. And so that is what I would expect. S equals 1, m sub s equals 1, 2s plus 1 is 3. The user enters 3 into the program. So you can have to watch out if I do have molecules with high symmetry. O2 has a high symmetry to it. Each oxygen's equivalent and they're in a line, and that gives me a high point group symmetry. And that high symmetry can give me degenerate orbitals. And when I get to degeneracies, here or in atoms, we did C2, is the same kind of a deal. Atoms or diatomics or things with high symmetry can give you degenerate orbitals, and there you have to really think about the Hund's rule. But if it's a bigger molecule and there's not degeneracies, and if you're lucky, then just see if all the electrons are paired and then it's a singlet, or is there one unpaired electron and it's a radical and then it's a doublet, and that will account for a great majority of cases. Some exceptions to this rule would include transition metal complexes or diradicals, and I'll talk about those next time.